All right, chemists. Well, welcome to another edition of the A-level Master Chemistry class. All right, and in this edition, I wanted to. All right, I'd hit the record button there, chemists. All right, so anyway, welcome to another edition of the master class in A-level chemistry here, and here we are with. In this session, what I wanted to do is I wanted to do some synthesis type questions. I wanted to wrap up our discussion of benzene. All right, so I wanted to go over some synthesis type questions that you'll probably see on the exam. Now, they're a little bit more challenging. They do bring in quite a bit of chemistry, you know, the mechanisms and the 6 markers and everything else. And so without further ado, let's head over to BitPaper here. So BitPaper, all right, our good friends at BitPaper there, chemists, making a really solid product. All right, and so here we are with this one. All right, I just like BitPaper. It just seems to be like a lot more stable. All right, and we're actually able to do something with it. So here we are then, right, to get my video feed and all my little bits and bobs in the background out the way there. All right, so this one here then, it says outline mechanism of the reaction of, let's see, 1, 2, 3, 4, that would be propanol with HCN and name the product. All right, so here we are then. 1, 2, 3 carbons. I can probably get my CH2s look a little bit better than that. Try it again. All right, CH3, CH2, CH2. No, look, the reason you can see it as an aldehyde is because this one here, I'm always asked this question, not only by year 12 student, like, you know, how it comes an aldehyde and not an alcohol, because the CHO is indicative of an aldehyde, whereas this one here, if I did COH, it's going to be obviously an alcohol. All right. Now, here we go. This one then. And I think there's somebody pulling into the car parking lot. There's the dogs and start barking in a minute. But anyway, look, this one here, this is 1, 2, 3, 4 propanol. And the reagent that they're going to use is HCN. All right, in reality, chemists, you would never use HCN. This is hydrogen cyanide. Absolutely not. I don't think any chemist in the world would use HCN because it's extremely dangerous. All right, when you put it into water, it produces hydrocyanic acid, which is extremely poisonous. And so you would never actually use HCN. All right. But they are going to allow you to produce the nucleophile here. Now, chemists, on this side of here, on this bit of scratch over here, I wanted to talk about nucleophiles really quick. And I wanted to tell you how to correctly draw the nucleophile, okay? So if you do this, if you do CN minus, this is wrong. All right, because you didn't put the lone pairs in. So no lone pairs, the LP. If you did CN and minus like this and with the lone pair on left-hand side, all right, this is wrong because the minus sign has to be on the lone pair, please. And so this is the correct way of writing the nucleophile if it contains a negative charge. All right, so here we are like this. This is wrong and this is wrong here. So let me switch over to Air Force Blue. All right, and oh, don't go find Air Force Blue like this. All right, here we are. Delta plus and delta minus. And so if you're thinking, And I'll keep this going. This to me, from our good friends at Bit Paper, they give this color. This to me looks like Kermit the Frog green. So I call this Kermit the Frog green. So look, 1 point for the correct way of drawing the nucleophile, the other point for the correct way of putting in the delta plus delta minus, and then this is royal blue. Look, lone pair goes up to the carbon. Now, chemists, what you're thinking is, I know it looks a little bit, well, you know, nitpicky, but the arrow, the head, the tail of the arrow starts at the lone pair and it goes up to the carbon like this. It says the third point, and then what you got to do is you've just got to then middle of the bond up to the oxygen. All right. So right now we're just racking in points. Look, middle of the pi bond there up to the oxygen. And so you end up getting, all right, let's say back into this color here. All right, here's your intermediate like this. Now, all you got to do, chemists, is literally just follow the arrows. All right, the negative the negative lone pair is attracted to the positive, the slightly positive carbon. So you get this, and obviously you push some electrons up there, and so now it's negative, and then this comes in like this. Now, meanwhile, you then need to show that move my video channel out there. Look, see this minus sign here? Here's the H plus like this. Now, if you wonder where the H plus comes from, it's just inside solution, all right? Because obviously your HCN is going to break apart into H plus and CN minus, isn't it? You know, the acid is going to ionize like this. All right, then. Now, this is the bit, and I'll do this one in red, chemists, all right? Electrons flow from the negative to the positive. So from the lone pair all the way over here. All right, in other words, you start the oxygen, the lone pair on the oxygen, and you go to the hydrogen. It's not the hydrogen going to the oxygen. All right, otherwise you'll just lose a mark. So I put this in because this is our tripwire here. All right, the light button this one in for this very reason. And so you end up, chemists, you end up getting this. All right, to finally, to finish this off, here we are, right there. 1, 2, 3, like so. All right. Now, this then, all right, is what we got in the name of the product. So let's see if we can, actually, hold on. Can I just do this? And I'm going to highlight it. Ooh, in. Now, right here, I'm going to do this in orange. All right. If you follow American football, I think this is the, is it the colors of, is it like University of Florida or Syracuse, one of those football teams? But look, you got to follow the longest chain. Oops, hold on. I needed to hit, after I picked my color, I need to hit the highlighter button, didn't I? And so is this now going to allow me to, hold on, right there. Maybe it will, maybe it won't. And I would give it a shot, but look, no, it's not. All right, never mind. Look, you just got to follow, the longest chain, please, chemists, that includes the functional group. All right, so 1, 2, 3, 4, 5. All right, and then if I change back into red, now see, I'll do it pink. If I change, look, we'll talk about this in an upcoming lesson. This one here, this is carbon number 1 because it's the highest functional group that you can have, you know, compared to the alcohol and compared to the alcohol and compared to the alkyls. And so this is going to be carbon number 1. There you go. Carbon number 2, 3, 4, 5. All right. So this would be, and I'll keep it in pink to spice things up. Second carbon in. this would be 2-hydroxy, like this. Now, if you're wondering why it is a hydroxy and not an alcohol, hold on a minute, 2-hydroxy whoops, I can write propan a little bit better, not propan nitrile like this. It's because the OH, all right, if this cyanide group wasn't there, this would just be an alcohol, it would be an ol. But because the cyanide group is there, the cyanide group has priority over the hydroxide, well, then you end up, the hydroxide drops down and you end up being, the main one is a nitrile, and so the alcohol group becomes hydroxy, and of course it's on carbon number 2. So this is why it's 2-hydroxy propan nitrile. Now, on this one then, chemists, let me turn back to this color right here. Okay, outline mechanism for the reaction of methanol. Now this one here, chemists, this is it's the propenyl chloride, 1, 2, 3. Now, this is how I teach us. Say, well, look, here is your mechanism like this: CH3, CH2, C, double bond O, Cl like this. And if I change pen colors to Air Force Blue, like to keep things color coordinated, then this is delta plus and this is delta minus. So in other words, chemistry, straight off the bat, very first thing I'm doing is I'm putting in delta plus and delta minus like this in the carbonyl because I want that point. All right, let me go back to came with the frog green. All right, say thank you very much. To examine it, I'll have this one. And then in comes, all right, in comes my alcohol. And so again, how I draw it is this. Look, I just draw it like this. Oxygen, here's your CH3 group coming off. That's a 3. And here's hydrogen like this. And so you go 1, and you go 2 like this. Got to put the lone pairs on the oxygen. So you're thinking, right, nucleophiles are a species that can that have a lone pair, that can donate a lone pair, all right, to form a covalent bond. As you're thinking, right, so here's my lone pairs on my oxygen. So you don't have to memorize all of the nucleophiles, chemists. You know, you've got your ammonia, you've got your hydroxides, you've got your cyanides, and the list goes on, like hydrides and everything else. But you're thinking, if you know that a nucleophile is something that contains a lone pair on it, then you're good to go, right? One less thing for you to memorize. You'd say, right, I can use this. And if you understand, it's just following the arrows. This goes up here, and this goes up here, all right? And so then you're thinking, right, boom, like this. Again, look, so nucleophilic substitution here. All right, I'm just going to create the intermediate. Actually, let me write that a little bit neater than that. I'll keep my alkyl chain together, right, like this. Boom. Still in the same color, like this. Right. All right, ding, ding, ding. Right. All right, here's my minus sign, Cl. Now, the reason why they enjoy putting this one in, chemists, is because of what happens with the alcohol. Now, look, if it comes down like this, all right, do you notice on this side, overall, it is neutral. The delta positive and the delta minus cancel out. And so I've got this. Now, when this lone pair, because the methanol is neutral, it's donating a lone pair of electrons in to the carbon. This is actually, if anybody ever asks you, this would be a dative covalent bond, because I am donating both the pair of electrons into the carbon. All right. And so when I do that, because I'm donating the pair of electrons into the carbon and it doesn't have a minus sign on it, like up here, had a minus sign on up here, right, chemists? Then this becomes positive like this. And then you push the pi bond electrons up to the oxygen. Now, when they fall back down to give you the carbonyl back, you know, of a choice. You're thinking, I've got to get my cup of coffee here. Look, you're thinking either, actually it was tea, anybody's keeping track, right? Either the chlorine leaves or the alcohol leaves, right? The chlorine leaves middle the bond up to the chlorine. Why? Because it is a good leaving group. Hold on, I can write good better than that. Hold on. All right, it is a good leaving group. And the reason for that is it's more electron negative, right? So you think in Pauling scale, chlorine is more electron negative than oxygen, therefore it's going to take the electrons, just leave, all right? But this positive sign, you have to get rid of this positive sign, right? Well, when the chlorine leaves, and in fact, let me hit this paper here and see if I can scroll up right there. Hold on, can I scroll? So, oh, I can. Right, look, when the chlorine leaves, the next thing it's going to do is it's going to, obviously it's inside solution. Look, it floats around, and I always draw my chlorine radicals lone pair minus sign on top because, you know, I said about the way to draw nucleophiles, same thing. It's just a habit. It's like minimize the bandwidth, chemists. Just put the minus sign on top of the lone pair. Right, back in Air Force Blue. Right, this one is then going to attack the hydrogen, and then this falls back down. All right, so you end up getting this right back into, I would call this teal green. All right. This. Right, so what we've done is we formed the ester. All right, and so I do believe that it said somewhere that we had to name it. All right, and so methyl, obviously methyl. Now, the reason why chemists, you know, thinking, look, you just got to start thinking like a teacher, right? The reason why they do the 3 carbons on the right is that they're trying to catch you out. All right, 1, 2, 3 carbons is 3 carbons is propyl. Yeah, you know that from year 12, right? And so this therefore is going to be methyl propanoate. So you're thinking the reason why they're putting this question down on the test, chemist, is simple, is because they're trying to catch you with the name at the end, you know. And so if I do in red here, right, tripwire. I always like, you know, using the phrase tripwire, watch out for the 3 carbons, especially this one. What they're hoping that you don't see is you don't see the 3rd carbon, which is the carbonyl. All right. The other one they're hoping that you don't see is this bit here. You know, where you actually, the chloride ion comes in and picks up the proton. This is your other tripwire. So, as I was saying to my students, look, it isn't the number of questions that you do. It isn't the number of past paper questions you print off and do. It's what you do with the questions. Like, you stop and you analyze it from all possible different angles. You think like a teacher and you go, yeah, okay, why are they asking me this question? What's the tripwires on it? All right. So anyway, this was first bit right there. And so right there, if If I pull this back in, all right, this is just our review of nucleophilic substitution then. All right, like this. Okay, now, meanwhile then, well, we've got this one. Now look, the reason why they did it is because in 1A and 1B, they're talking about nucleophilic substitution, right? But on this one, no, this is the electrophilic addition, but they're hoping that they're going to catch you out on it. Now, they're hoping that you think this is also nucleophilic substitution, because we've been talking about the last 2 or 3 lessons here. It's not double bonds in the ring, it's delocalized pi bonds, okay? So anyway, it says right here, give the formula of this reactive intermediate. Well, all right, on this one, chemists, this is how I look at it. And so, hold on, don't know about red, it's a bit, you know, standoffish there. So let's just go back to teal green, start this, like boom. Ding, 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 ding. All right, then. So this CH3, all right, C double bond O, Cl. Right, naming time, 2 carbons. So this is my ethanoyl chloride, like this. Okay, now I'm going to react it with aluminum chloride, and I think we went over the mechanism of this last time. And so what I'm going to form is I'm going to form like this my electrophile, like this. This is my acylium ion, and obviously AlCl4 minus, right? I mean, it's easy to keep track of. I mean, you know, positive, minus, or you just take off the chlorine in your mind. You're thinking, yes, just a good leaving group. Okay, and we went over the mechanism of this in like the previous lesson. All right, so anyway, the form of the reactive intermediate would be this. So I'm just going to write down this. And my hint for doing these type of questions is this one then, right? You're thinking, look, this is, you know, your typical electrophilic substitution, right? On the first 2 questions, part A, part B, was nucleophilic substitution. Now it's electrophilic substitution. And so you use an electrophile which has a positive charge on it. So have you ever taken the exam and you're going, not on, forgot what I'm doing here. I think, no, as soon as you see a ring system like a benzene, they tend to stick to benzene, right? You go, no, it's electrophilic substitution, because those aren't double bonds in the ring, they're delocalized pi bonds, okay? And so therefore I know it's going to be positive, whereas the other one with the carbonyl, that was nucleophilic substitution, right? All right then, so on this one then, so now what they want to know is the mechanism. And so I'm thinking here, chemist, my mechanism, right? Now, as I mentioned in the previous lesson, chemists, when you're doing this, stay away from the Kekulé structure, please. Why? Because Kekulé structure, I don't know, it's kind of like the slippery path. You're going, yes, all of a sudden you may start to think it's a double bond. The examiner may think you start to think it's a double bond. If you do a ring, it's kind of like in your mind, you've got to like separate it out. You go, no, ring means delocalized pi bonds. And so this right here and right here, this is, now I'm going to draw it like this. This is my acylium ion like this, all right, the positive on it. All right, now, how do you know this is the acylium ion? You're thinking, well, it's easy, chemist. This is a Friedel Crafts acylation. All right, so if you're thinking Friedel Crafts acylation, like this, which is what it is, acylation and acylium. So is it 2 L's? It is now, it is today, acylium ion. Well, they tend to, like, you know, they sound similar. All right. Now, Chemist, back into Air Force Blue then, what we've got to do is this one, boom. All right, see this? Now, do you see how I drew that? Middle of the ring, Chemist, middle of the ring. In fact, I had mine almost touching the little circle in the middle there, right? None of this, oh, is just on the edge of the ring there. It could be, looks like it's coming from a carbon. No, do you know? So I carefully made it between the two bonds there in the middle of the ring. Okay, and so I got this one. This is the point, and I've got to put in my delta plus and delta minus because it's the habit. Actually, don't need my delta plus and delta minus on this one. Let's do like this, right? Like this, like delta minus, because this is the whole positive charge. And then middle of the bond, please, up to the oxygen. Right. And so, arrow, what I got now is I've got this. Now, what you've done, you know, we talked about this the other day. It was like, yes, you've broken the ring system, the conjugated pi bond system, right? Then where you add it is going to be positive. And I'm really picky about this, chemist. The broken ring goes all the way around, and it doesn't, kind of like making a shape like that. It does not go over the positive sign. All right, like this. And then you've put on, actually, you know what? I don't need to push those electrons up. So let me just do this. All right, get rid of that completely. All right, so look, you've now got this. Ding, 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 like this. Right. Now, did you notice how the positive charge on the carbon, on the acylium ion, has now moved over to the ring? Now, it's assumed going around the ring, there are hydrogen bonds coming off, right? Each carbon is attached to a hydrogen. And so you do this. Now, hold on. I can draw a hydrogen bond slightly better than that, chemist, like this. Now, like this. Now, you're thinking, now you need to reform the ring. Why? Because it's more stable. You know, we talked about the resonance stabilization of benzene. We said is it 152 kilojoules per mole? Right. So bottom line is that this, now look, and I'll do this in Air Force Blue so that you can see it like this. Middle of the hydrogen bond, please, chemist, over to the positive charge inside the ring. All right, so write this down. Middle of hydrogen bond to the positive sign in the ring. And the reason why we're doing that, chemist, is because it's got to be middle of the bond. This is best practice, okay? And you are showing that those electrons are reforming the ring by going to the positive charge. None of this, the examiner thinks so. Could it be on top of the carbon? No, in the ring, all right? And when you do that, you reform the ring. So I'm going to do it like this. Actually, because my video feed is right there. Oh, maybe you can squeeze it like this. Look. Reform ring. And then you've got this, like so. Right then. Now, chemists, so far we're doing all right. You may be wondering, well, why does the hydrogen just decide to donate its electrons to the pair? Because, all right, and this is best practice that you do this, okay, is this, look. You got chloride ion, but my, I always draw them like this. Look, my chloride ion, I don't like the way that arrow looks. Hold on, can I just do it again? I hope so. Yes, I know. Hold on. Like this, look. The chloride ion attacks the hydrogen, donates it in like this. Right. And then you've got this. Right, so I formed the ring. Now, The reason why I mention this is that you know that AlCl4 minus, all right, is what we were left with when we formed the electrophile in this equation here. Here's my AlCl4 minus, where you know the catalyst has to be regenerated. And so you just do this. This is a proton from the ring that it picked off. And you have AlCl3 and HCl. In other words, you've regenerated the catalyst. Oh, I do like bit paper. Now look at that. That is lovely. Right, regenerated the catalyst. I was writing really quick on my tablet there. Okay, just testing it out. All right then. So you're thinking, good. So this then is a quick review of Friedel-Crafts acylation reactions right there using an acid chloride. All right. Now, oh, yes, this one, right? Now, this one here, let me get my tea here, chemists, all right? Now, chemists, it looks a bit foreboding, doesn't it? You say, oh my goodness, I got all these structures and I got arrows going everywhere. How on earth can I possibly figure this out? Answer one step at a time. Okay, and so step one then, if I draw, you're like the old adage, how do you eat an elephant? One step at a time, one bite at a time. Well, then there you are. And so if I draw the actual mechanism out like this, ding, then this is the actual step, right? You're thinking, oh, hold on a minute. It's not so bad because you chunked it down into individual steps, right? So I'm just focused on step one right here. So I've got methyl, right? And we know let's pick a color. Oh, this is Florida orange right here. This one right here. Yeah, right there. So this one here, then slightly different shade of orange. All right. So my methyl is, it's a para director, meaning that, in fact, I think it's an ortho para director, if I'm not mistaken. But anyway, look, methyl, it's going to direct the NO2, the nitro group, to the para position, like this. And so now you're thinking, right, okay, so hold on. Methyl, para director, this is why the NO2 is over here. And how do I put an NO2 onto a methyl group? Well, it's got to be a bit of nitric acid and a bit of sulfuric acid. Because remember, in like the previous lesson, I said what you need to do is you need to memorize this equation, right? So anyway, for the reagents, all right, so what do I need for my reagents? Well, I'm going to need some nitric acid and I'm going to need some sulfuric acid. Why? Because I need to generate the electrophile. Now look, what you're thinking is, again, just don't do the questions like really quick. You know, if you do them under exam conditions, well, that's one thing, right? But if not, you're thinking, slow down, think about each question, what they're asking you. They're asking you for the reagents, and you know, benzene ring, you've got to be able, it's got to be to generate the electrophile. Like this, yeah? And so this is how I keep it straight in my head. Benzene ring, electrophile. Oh, I've got this. And so my equation, now chemists, there's more than one form of this equation. I think there's one where you generate the H3O plus sign. Look, I just keep it simple. All right. save a bit of bandwidth, you know, as in that bit of space in your mind where you're solving problems for a more difficult problem. So if I've got nitric acid and sulfuric acid, right, I know I've got to generate my electrophile, which is my NO2 plus, like this. And hold on, it's supposed to be a plus sign. And so I have to take off, well, if I look at HNO3, what I've done is I've taken off a hydrogen and I've taken off an oxygen and, you know, I made it positive. And so hydrogen, oxygen, I'm thinking water. All right, and where's the other proton coming from? It's coming from the sulfuric acid, right, HSO4 minus. Now, yes, I do realize that that is not the mechanism by which this goes by. You know, I know it's like, you know, Bronsted-Lowry and proton transfer, but you know what? If you just want to memorize the equation in your mind, this is it. Now, let's see then. So for this one, boom. All right, did I actually answer the question? You get the reagents, yes. Write the equation, yes. Okay, so now it said, I can move my video link there. Name and outline the mechanism for the reaction between this inorganic species and methylbenzene. All right then, so, well, here we are then. So name of mechanism then. Let's see, it's got to be my electrophilic, hold on. Got to be my electrophilic substitution there, right? Now, substitution. The reason is because I'm going to substitute an NO2 for a hydrogen on the ring. It's an electrophile because it's got to be, because the ring doesn't have double bonds on it. So therefore it's electrophilic substitution as compared to the previous question with the carbonyl, which was nucleophilic substitution. Okay, and so this one then should be fairly easy to do, like this, yes. And then, hold on, what was I? Video link. What was I? Oh, the methyl, and that's a methyl group. So if it's a methyl group, just let me, this is my methylbenzene. Like this. And, you know, same exact thing, chemists, all right? So hold on, NO2 plus. All right, so in Air Force Blue, right, like this, middle of the ring, not the carbon, not the bond, middle of the ring, please, chemists, out to the NO2 group like this, and you end up, all right, now, because we know the methyl is a para director, so I'm going to put the positive sign there, obviously, right? Here's my broken ring like this. Here's the hydrogen, which I'm going to attack next. And then here's my NO2 plus, like this, floating around. And then back in Air Force Blue, all right, ding, like this. Middle of the bond for the hydrogen, going back into the positive charge in the middle. I'm reforming the bond. All right, back into teal green. And so you end up then with this. NO2, which I believe was what they wanted in the question. Right, now then, in case you're wondering, you think, but hold on a minute, hold on. How did you get the hydrogen to donate its electrons back in? Because guess what's floating around? Right, is, and I'll do a rather large arrow like this right down here, is your HSO4 minus ion floating around. Yeah, negative, it's going to pick up the proton. And then when you do that, what you've done is you've regenerated the sulfuric acid, which was the catalyst, right? Yay. So you're thinking, got it. All right, then. So, do you know as chemists, like a quick recap, we would go on to a different question was, hold on. Right, so look, started out, the reason why I picked this question, you got your nucleophile over here. The correct way of writing a nucleophile, yes. And I'll put this in. I will come at the frog green. It's the correct way of writing it. All right, number one. So a quick review of how to write a nucleophile. Here's my nucleophilic substitution. The point you got to put in nucleophile, arrows middle from the lone pair up to the carbon, push up the pi bond electrons to the oxygen. Partial charges, delta plus, delta minus. Here's your intermediate, right? Your intermediate. This is the tripwire lone pair to the hydrogen, which is inside in solution, giving you your hydroxypropanenitrile. Went over the fact that the nitrile is a higher priority group than the hydroxyl, the alcohol group there. So this alcohol group drops down to being a hydroxy. All right, tripwire, 1, 2, 3, 4, 5 carbons, longest chain, including the cyanide, the nitrile group. Done this bit. You have 2-hydroxypropane nitrile. And then we also did the one, all right, with my acid chloride, nucleophilic substitution. They put in an alcohol just to go and see what you would do with it. And it's like, yes, you know what to do with it. It's got a lone pair on it. Boom. Same thing, you know, lone pair, arrow, delta plus, delta minus. Push up the pi bond electrons to the oxygen, right? This forms back down. This, the lone pair and the oxygen reforms a pi bond. This halogen leaves. Why? Because chlorides, this halide leaves. Why? Because chlorides are good leaving groups, very electronegative. All right. And again, you need to show the fact that the chloride coming in that was left off, went left over here as a leaving group on the acid chloride, electrons going from the lone pair to the hydrogen, and you reform you get rid of the positive bond there. And the reason why they like doing this one, chemists, is because of the 3 carbons on the left-hand side. They're trying to get you caught out. They're hoping that you think this is ethyl. No, it's not. It's propyl. All right, then. Now, flip side of it, then, this is the electrophilic substitution. Right, a quick review on how to generate the reactive intermediate. Okay, which was just my acylamion here. This is electrophilic substitution. All right, then. Now, meanwhile, ethanol chloride, right there, and my reactive. Oh, this is how we form the reactive intermediate, the electrophile, right there. Let's see if I come down to here. All right, so then they wanted the actual mechanism. All right, arrow, middle of the bond, the ring, the circle, out to the positive charge on the acylamion tie-in. Acylamion and acylation, they sound awfully similar. Right, best practice, when you reform the ring, arrow, middle of the carbon-hydrogen bond to the positive charge on the reforming the ring. Why? Because the chloride, all right, that fell off, the acid chloride is now going to attack the hydrogen, reform the ring. Why? It's more stable if it reforms the ring. And so therefore you've got your product over here. I move my video feed out. So this is phenylethanone. And then of course you got to regenerate the catalyst. Now, if you're wondering why it is phenylethanone, well, that is because right here, all right, in teal green, all right, so look, if I do this, down here, look, chemists, right. yeah, this is a ketone, obviously, right? So you're thinking, this is how I teach it. I say to my students, look, if it was this, I don't know, I can draw a math a little better than that. Hold on. If it was this, yeah, you would call this a ketone, and you would say 1, 2, 3, right, Graham, this is propanone, right? Mm-hmm. All I've done is I've replaced an alkyl group with an aryl group as ARYL, and this is no longer propanone. Just because I've replaced the alkyl group with an aryl group, it then drops down. It's no longer benzene. All right, this is not benzene because it is attached to, well, essentially carbonyl. It drops down, it becomes phenol. Yeah. Why? Because the carbonyl group is higher priority than benzene in the ranking of substituent groups. Okay. So this was this one. I hope it was a nice in-depth analysis. Okay. And then we did this one, right? Again, generate the electrophile. All right. The reason why I picked this one, chemist, is because it looks a little bit foreboding, doesn't it? You know, it's like, oh, all these steps everywhere. No, just chunk it down step by step and you'll be all right. All right. So, you know, step 1, 2, 3, 4, step at a time, chemists. So I'll call this step 1. And then if you look at it, you go, oh, yeah, right, got it. All right, then. So let's say this was the mechanism we needed here. And the reason why I put this one in is because you need to show that you can regenerate the catalyst, which is your HSO4 minus ion. It's going to pick up the proton and regenerate the catalyst and close down the ring and everything else and reform the ring. Right. Now, hold on, step 2. Let's see. Hold on, I have to go back and look at the question after that. Bit of a vamp there. All right. So, okay, now this one, chemists. Right. Now, what I've got is I've got my nitro group here, and it's being reduced down to an amine. Okay. So let me come down to this one here then. All right. So hold on. So I do it down here. So look, what I got is this. This is, I'll do it up here. Look. Arrow. It's being reduced down to an amine like this, right? Like an NH2 group. Okay. So what I'm thinking then is, yeah, this is a reduction. Okay, because you know, oxidation is losing electrons, gaining oxygen. Probably did this in year 12, right? Oxidation is losing electrons, gaining oxygen. Reduction is gaining electrons or losing oxygen. So we've gone from NO2 down to NH2. So we're thinking, okay, why is the examiner asking me this one? Because what they're hoping that you put down on the test, chemists, is this. And put down is not. All right. They're hoping that you think, oh, hold on. Yeah, reduction. What, isn't that sodium borohydrate? Or is it what, like lithium aluminum hydrate? No, yeah, this one had to be an ether because it's extremely reactive in water. And I think this one is just in water. I think this is aqueous. Right. Answer, no. Right, this is how you reduce. This is how you reduce what's known as aliphatic, as in straight chain, amines. aliphatic NO2, right? As in straight chain. Yeah. Not, and I'll do it in chromatograph green. So in other words, the sodium borohydrate or the lithium aluminum hydrate, tell you what, this is a better example here. This is the one that you used for, wasn't it the carboxylic acid going down to the aldehyde, going down to the alcohol. Yeah, like this, hold on. Right, you know, like your primary alcohol, your secondary alcohols, right? So this one, this up here is, you got to think, this is a ring system. So I keep it straight in my mind. So I think sodium borohydride, or lithium aluminum hydride is carboxylic acids down to aldehydes down to primary alcohols, or aldehydes down to secondary alcohols. Ring system, you've got to be using something different. It can't be the same thing, because you're thinking, why are they asking you the question? To go and see if you know that this is when you use tin and a drop of acid, or you can use nickel and hydrogen. All right, either one of these, right, in your mind, in your notes, tie into the ring system, please, chemists. Okay, now, meanwhile, then, they said, give the reagent step 4 and state a condition to ensure the primary amine is the major product. Well, let's have a little look. Okay, so here we are then. All right, so on this one, okay, I got this going into that. Hold on, gotta get this down. So it was, I'll do it over here. Right, so my short-term memory is good. Was it this? And it goes into this, right? Okay. Well, the reagent, the only thing that I can think of, chemist, the reagent, well, I see an NH2 there, and I'm thinking it's got to be ammonia, right? So I'd write down this, ammonia. So this is the first thing I would do, ammonia like this, yes. And now look, you're then thinking, state a condition to ensure that the primary amine is the major product. Okay. You know, in year 12, you know, in year 12, when you did, in year 12, you did your very first nucleophilic substitution reaction, and, you know, you did the one with hydroxide, you did the one with cyanide, you did the one with the amine, and then you probably learned this mechanism that is kind of like, yeah, if you're not careful, you know, you try to generate just one amine. You got to be careful about. You got to be careful about the product. You know, like you can generate the primary amine, the secondary, the tertiary amine, or the quaternary salt. If you have excess, if you have things like excess reagent, I think it's amine. All right. So bottom line is, you're thinking this is the one that comes to mind. So I'm thinking amine like this, and a condition to make sure that I got the primary amine is the major product. I would write down that it's excess like this, because this is what comes to mind. All right. So again, chemist, you know, when you're doing this, right, just like start in your mind, just like putting it together, think, okay, well, back in year 12, I can recall doing the one with the alkyl halide and the amine, and if I wasn't careful, I would have, I could hit the primary amine all the way up to the quaternary salt. And so if I didn't want that to happen, what I'd have to do is I'd have to increase the concentration of the alkyl halide and decrease the concentration of the ammonia. Well, in this case, I want the primary amine to be the major product. I want to force the reaction all the way over to the right. The only thing I can think of is making excess, the condition excess amine like this. Now, name of mechanism. Well, my amine is definitely a nucleophile like this. And so it's going to be a nucleophilic like this. And I'm just looking at this equation that they gave us up here for step 4, right? I see the chlorine right there is being replaced by the amine. All right, so it's going to, arrow's going this way. You can put down the NH3 replaces the chlorine, so the nucleophilic substitution. Now, like this, right. So I'm thinking mechanism chemists. Well, again, look, just write down what we know. Here's my ring, here's my CH2, and I'm going to draw out. Actually, let me draw the CH2 out like this. Carbon, hydrogen, hydrogen, chlorine. And you go, oh, yeah, got it now. Because look, you know, this is delta plus and this is delta minus. And then here's my amine come along. It's my neutral nucleophile like this, arrow. And so in Air Force Blue, I like keeping things color coordinated, you know. Lone pair attacks the carbon right there, pushes the electrons up to here. And so I end up on, got to turn back to teal green here. All right, and I'm actually going to tidy it up just a little bit. So what I wanted to do is put my amine, put my amine down here, my ammonia down here, like so. Here's my lone pair, and then put this arrow going down to here. And the reason why I did that is because, well, I want to draw my arrow in, because you know, when you do that, I'm going to get this. So I can get my carbon like this. Let's say like this, and then here's my nitrogen like this, and I've got 1, 2, 3 hydrogens coming off it. Now, chemists, you know, lone pair being donated into the carbon. Right, this is my dative covalent bond. And so, because it's putting the lone pair into the carbon, this then becomes positive like this. It's supposed to be a positive right there. All right. This is what you need excess amine. Well, guess what? Here comes another amine, and in Air Force Blue, right, it just attacks the proton, and then this falls back down like this, and so you end up getting this. In fact, I can just draw this out now like a CH2, right? Like this. CH2, NH2 like this, all right? Which is what they said happened in step 4. Now, chemists, look, the reason why I'm doing these synthesis questions with you today is this, is because you know what a nucleophilic substitution reaction is. You've done this reaction in year 12 with alkyl halides. All they've done is that they've just put on, well, a benzene ring to kind of throw you for a loop, right? You're thinking, no, it's the same thing. As soon as you see the carbon-chlorine bond, amine, nucleophile, you're thinking nucleophilic substitution. All right, you know it's a dative covalent bond coming in, and it's got a positive charge on the nitrogen, and so therefore you end up, well, forming that. All right, now, ding, ding, ding. Let's come down to this one. Okay, so this one, chemists, look at the clock. We did this one last time. All right, so I'm just going to skip this one for right now. Okay, because I wanted to focus on synthesis questions today. So it says benzene can be converted to amine U, right, with a two-step synthesis shown below. All right, the mechanism of reaction 1 involves attack by an electrophile. Give the reagent, you produce the electrophile needed in reaction 1, and then write an equation showing the formation of this electrophile and mechanism. Now, the reason why I picked this one, chemist, is because it's what we know, but in a slightly different format. Okay, they haven't given you everything, you know, like this is the first graphic, you know, like say step 1, this is step 2, and this is step 3 and step 4, and they've got all the images up there for you to go look at, giving you a hint. This is more just kind of like a 6-word type question, you know, like a 6-pointer. So you're thinking, all right, but we know what to do. And so on this one right here, so you're thinking, right, we'll just do this like this and say, right. Here's my benzene. So immediately I'm thinking electrophilic substitution, because benzene, nitro group. So I'm thinking it's got to be this. All right, it's got to be HNO3. All right, and H2SO4, because this is going to generate my electrophile like this. All right, here's my NO2 plus floating around, arrow like this. All right, middle of the ring. Yeah, I mean, we can do this one fairly quickly, chemists. I just wanted to show you a very similar question in kind of like an essay format, a word format, not everything chunked down. All right, put the positive there. Broken ring, we know it doesn't go anywhere near the positive. Right. Here's my electrophile stuck on. And so hydrogen, and we know that the hydrogen in Air Force Blue is going to, again, I can draw that a little bit better. Look, try to get to land on top of the positive inside the ring, chemist, so that the examiner knows you're not putting it at the carbon down here or anywhere else. It's inside the ring. He knows you're showing the ring being reformed. And so therefore you end up getting this, right? So this is just the nitration of benzene, okay? All right, the reagents used to produce the electrophile needed in reaction 1. All right, well, again, this one, and I tell my students, chemists, look, what you got to do is got to write this out numerous times so that you just commit it to memory, because this is on the test every year. Nitric acid, sulfuric acid is going to give you your electrophile and water and HSO4 minus, like this. So this is the reagents right here. I've done that. Reagents. Write an equation. Oh, actually, should I just call reagents this? Yes, the reagents then would be nitric acid and sulfuric acid. All right, the equation. Okay, forming this electrophile, done that. This one down here. Okay, outline a mechanism of this reaction with electrophile with benzene, done that. Right now, got to show the regeneration of my catalyst there, like this. And so this is going to attack that. Now, the reason why I do this, chemist, is because, look, it's not hydrogen. You know, you're thinking, oh, I'm sticking the hydrogen back onto the HSO4 minus to reform the sulfuric acid. No, the negative charge is on the HSO4 minus. The arrow starts at this compound, HS4 minus, and ends on the hydrogen, please. Okay, so there's this one. Just checking things off as we go along. Right. Now, this one then, you're thinking, cyclohexene. Now, as soon as I see cyclohexene chemists, right, I'm thinking, no, it is not electrophilic substitution, because electrophilic substitution is the flip side of the coin for nucleophilic substitution, which involved electrophilic substitution involves a delocalized pi bond system, right? No, it's not that. So what it is then is you only have one. This is actually a double bond here. It is, right? So it says suggest a identity for compound V. Now you're thinking, okay, I got this. I've got this, right? Arrow. Some mystery compound which has to still contain a ring system, I'm taking a guess, and goes up to phenylamine, this right here, right? And so you're thinking, well, I just can't stick the NH2 onto it. No, because this would be if it was a delocalized pi bond system, like a benzene, you know, like benzene and the nitro group gives you nitrobenzene. No, you can't do this one this way because you don't contain a ring system. So I'm thinking, but NH2. How can I, what is linking in my mind to NH2? Well, I'm just taking a guess. Ammonia has got to be in there somewhere. Okay, this is something that I would consider, right? Ammonia, okay. So I'm thinking, right, ammonia is my nucleophile. So therefore, I wonder what could possibly, a nucleophile, hold on, alkyl halides in year 12, yeah. Hold on, chemists, nucleophile NH3, could that attack a carbon with a halogen on it, you know, like an alkyl halide? Yes. Oh, so therefore, could I don't know, somehow stick a bromine on it? So you see what I'm doing, chemists, is what I'm getting at is I'm starting at the end product and I think NH2. The only thing that comes to mind is NH3. Then I go, right, this is the nucleophile, right? Okay, nucleophile NH3. That can attack, I'm thinking alkyl halide, year 12. Could that possibly attack a carbon halogen bond? Yes, it could. Right. So now I'm thinking, hold on. Double bond. Remember when you did alkenes? Remember when you did alkenes in year 12, the double bond, and you reacted it with HBr, right? Remember you did the Markovnikov rule and everything else in year 12 with alkenes and HBr, right? I'm thinking alkene here, because this is what, cyclohexene. And some HBr right there. So my reagent right there would be HBr. Yes. Okay. And well, it's still a ring. So I'm thinking this is, well, it's a double bond, isn't it? So hold on. Let me write it down here. So I'm thinking the mechanism, could it be electrophilic addition, because the addition, because, you know, like HBr, but, you know, you got the hydrogen bromine bond, and yeah, the double bond in the alkene attacks the HBr, and then you stick the proton on, and then you got the carbocation, the bromine attack. So yeah, this is electrophilic addition. That was your 12 alkenes, right? So right there, reaction 3, done this. Reagent HBr, name the mechanism, electrophilic addition. All right, let's see. So now the reagent, right, ammonia. Now with ammonia, chemists, do you always notice that it always seems to be in excess? Yeah, kind of makes me think of the rock band of the late 80s, early 90s, in excess, but here we are. Right, in excess like that. This is the condition. It's the only condition I can think of for ammonia, right, is in excess. And name the mechanism. Nucleophile substituting for bromine. Would this be nucleophilic substitution, right? Like so, right then. Now, having said that, chemists, done this one. We're doing pretty good today, right? Explain why amine U, right? Why amine U, all right, is a weaker base than amine W. Okay, so hold on. Is it amine U floating around? Aha. So hold on, let's get the, right. Pull this back in from the previous tile there, right? Look, NH2 like this, yes. This is amine U, right? Amine, yes, this is phenylamine, is a weaker base than amine W. Right, so again, chemists know, look, on this one, the reason why I put this one into today's lesson is this. You're thinking, well, what's the only difference? The only difference between amine U and amine W is this ring. And this is, you know, a ring system. Actually, let me call it, can I just call this here's my conjugated pi bond. Yeah, it's a ring, you know, delocalized electrons, anhydridized p orbitals going around. And this is just a plain, well, alkane. I mean, isn't it? This is just a plain old garden variety cycloalkane. So I'm thinking, why would amine U be a weaker base than amine W? Well, the only thing I can think of is you got lone pairs on the nitrogen. Right. So I'm thinking, ooh, could it be this? You know, just thinking aloud now. Here we are in, do this color here. I'm thinking that the ring system, does this have to do with, I can draw a straight line better than that, hold on. Does this have to do with the negative induction effect? Remember, like year 12, you did like negative, right, that little bit better. In year 12, you did the positive induction effect and the negative induction effect, right? And we said the positive induction effect was when an alkyl group, the electrons flowed from the alkyl group to the carbocation. You know, like when you're talking about, say, primary, secondary, tertiary carbocations, right? The negative induction effect is when the electrons flow away from an electron negative group down to, in this case, a ring system. And so I'm going to say, why is it a weaker W, a weaker amine U is a weaker amine, a weaker base, and amine W is because, all right, amine U contains a conjugated, oh, I do like this pen, lovely, conjugated pi bond system, like this, yes, which draws in electrons from the nitrogen, yeah, whereas I'll put down, all right, amine W cannot do this. Now, when you answer these type of questions, chemists, you just don't state the fact. I mean, first off, you say, you have to state the fact, number one, and then do the comparison, number two. And then for the last point, you need to say, and this is the reason why you say what you say. So yes, amine U has a conjugated pi bond system, fact. Amine W doesn't. That's one point. So because it's got a conjugated pi bond system, this means that the electrons are going to flow from the nitrogen down to the ring system, negative induction effect, second point. And then you've got to add your third point, like so what, which is, and I'll write it up here like this. And so, I'm going to say the nitrogens are nitrogen, just nitrogen. The nitrogen is less, hold on, gotta make this nice and neat looking. Able to donate electrons. And, if you're thinking Lewis acid and Lewis base, isn't a Lewis base a species that can donate electrons? And so you're thinking, oh, I'll put down, it's going to be a weaker Lewis base. Now, you see that bit there, chemists? What I'm getting at is this, right? You're thinking, yeah, you need to state the facts, make the comparison, and then you need to explain what you see and put in some key buzzwords like, yet nitrogen is less able to donate electrons. Again, so what? So therefore, it's a weaker Lewis base because the Lewis base is something which can donate electrons, right? So let's see. Back into teal green here. All right, is it emerald green, teal green? Don't know. All right, the acylium ion, well, we know what this is. All right, it's down here, acylium ion. Right, CH3 plus, yes, is formed in the mass spectrometer by fragmentation of the molecular ion of methyl ethanoate. All right, write an equation with this fragmentation and include in your answer a displayed formula for the radical formed. All right, so here we are then. I'm going to put this and move this up here. All right, so this is our target molecule like this. Right, ding. Now, the reason why I put this one in chemistry is because, all right, so hold on, methyl ethanoate. All right, so, no, hold on, I got too many carbons. like this. Right. Methyl ethanoate, 2 carbons right here. So the 2 carbons, chemist, this is my ethyl, this is my methyl. And so a little review of nomenclature of esters. This then would be methyl ethanoate like this. Okay then. Oh, right, ethanoate better than that, hold on. Now, arrow, it said is going to deform this. Now, what I need to point out something, chemists, is this bit. You think, oh, well, hold on. Yeah, you just formed the acylation ion, yes. And, well, if I got this bit snapped off, right? And I'll show the tripwire now. Look. See this, right? This right here in orange. This is this bit, yes. All right, here's my acylation. What's left is this thing, which I'll do in, let's do it in, oh, I would call that pink chemists. Look, this. All right. Right, ding, 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 like this. Now, in pink, the tripwire is on this one. Is look, as soon as you see a mass spectrometer, you think +1 charge on the ions, and so it's my ethyl methanoate right there. My methyl ethanoate right there. See this bit? This thing has to be, all right, chemistry, square bracket around the side here like this. And you got to put a positive charge on it because it's going down the drift tube. Remember, we talked about time of flight mass spectrometer. Victor is a daft duck. You're thinking, right, it's going down. Vaporization, ionization, here's a positive charge here. This has to be positive, is going down the time of flight tube, okay? And so on this bit, I'm just going to, this has a positive charge, and this is okay. And then this bit snaps off, and so this has to have a radical right there. So you need to put on, you do need to put on the, actually, you know what? Just let me move this positive charge up here. I put this positive charge up here. All right. Like so. And because I snapped this bond, now you see this bond right there. I snapped the bond. Here's a carbon oxygen bond I'm talking about. Homolytic fission, right? 1, 2 electrons. One go one way, one go the other way. And so, yes, you do need to form the radical. You do need to show the radical being formed, right? One there, one there. Okay. And the hint, if you read the question, you're thinking radical, this means that you do have a low electron on it. All right. So anyway, this was A. So, but A is this bit here. This is A. And it said the acylation ion, right, can also be formed from ethanol chloride. This ion reacts with benzene to form this. All right. Well, we've done this like so many times, haven't we? But I'll just put this in. All right. It's a quick review. All right. Well, here's my ethanol chloride. So I'm thinking this. Hold on, I'm going right over here. Right. Ding, ding, ding. Actually, do this. Right. This is this bit down here, look. So here is my ethanol chloride. You'll notice, chemists, that they always keep the acid chloride's really easy. It's either ethanol chloride or it's like propanol chloride, right? So this right here, ethanol chloride. And yeah, I need to react it, AlCl3 like this, and it's going to form, I'm going to snap this off. I'm just going to form the acylium ion like so. And my AlCl4 minus, Cl4 minus, I can do a little bit better than that. Right. And there you are. So again, look, for 2 points, chemists, easy, point in the bank, right? Just memorize the equation, write it out a couple of times, you'll be okay. Now, ding, ding, I think, now I'm looking at the clock, chemists. Yeah, I'll just do this one really quick, you know, because I try to keep these like short by like an hour. All right, so name of mechanism, obviously, this is electrophilic substitution. And by now you're thinking, right, benzene like this, ring, and then here is my acylium ion like this. All right, Air Force blue. Okay. And draw the arrow going across. All right. Like this. And hold on, I've got to show the broken ring system right there. So positive, like this. And let's see, well, the chloride, lone pair like this. All right, negative sign on top of the chloride is just easier, right? Lone pair to the hydrogen. All right, hydrogen arrow going to the positive. Reform the ring, okay, because you're going to, back in teal green, emerald green, whatever it is. Right. You've got this. So by now, chemists, you're thinking, you know, you really should be able to do this mechanism. I wouldn't say without thinking about it, but you know what I mean. Like, you know, you've done it so many times. Okay. All right. This mechanism is here. All right. And the ethanoic anhydride also reacts with benzene. All right. So the equation then, this one. Now, the reason I put this one in chemistry is a little review of what we did last week. All right. When we looked at the acylation reactions, we did acid chlorides and we did acid anhydrides. All right. And so again, you know, you're just going to do the same exact thing. On this one, I'm just going to draw it out like this. I'm not going to do the actual mechanism. Right, this and that. And so you form, your product is this. Now on this one, chemist, because it's ethanoic anhydride, look, which is just, you know, 2 carbons, F. Like so, because you have done, all right, here is your acylium ion like this, right? This is this. Then what's left is, well, this bit, which becomes just the acid. Because if you've got this, look, if you've got this floating around in water, the minus sign on it, you're thinking, yeah, I just got to put the hydrogen on it to make ethanoic acid, okay? right then. Now, I do believe it's all I had for this week, chemists. And so hopefully you found this lesson helpful. All right. So what I wanted to do is a lot of synthesis questions. All right. Nucleophilic substitution, electrophilic substitution, show you how to break down the larger synthesis questions into, well, manageable chunks. Okay. So next week, what I thought we'd do next week is for my year 12 students, let's do a review of halogenoalkanes, all right? And so we'll do that next week, okay? So I split my time to year 13 to year 12, and so we'll do haloalkanes next week. All right, so substitution reactions, elimination reactions, and everything else. So chemists, have a good week, and I will see you next time. All right, so take care.